All right, let's take a little tour of the periodic table. So, all of the rows, we call those periods. So, we have the first period up here, second period, third period, and so on. The columns are called groups. All right, so you have group 1, group 2, just kind of goes all the way across, all the way to group 18. Older tables, it's like 1, 2, 3, 4, 5, 6, 7, 8, and then these inside ones had different numbers. Actually, there you go. You see the Roman numerals. Yeah, so there's like the A group and the B group. So, yeah, this is an old periodic table here. Some of these groups have names, and you should know those names. So group 1 is known as the Alkali Metals. All right, so hydrogen is in group 1, but it's not a metal, but it is in that group. Second group here, alkaline earth metals. The way I always kept that straight, because alkali metals and alkaline earth metals sound a lot alike, but alkali, one word. Alkaline earth, two words. So there's your 1 and your 2. And also alkaline earth. It's like the 2-word name as opposed to just alkali. So the longer 2-word name is group 2. Kind of weird, but it worked for me. Going over to the other side here, we got noble gases, also known like inert gases. I think I've heard a couple other names for them, but usually they're called the noble gases. They're called that because they're very unreactive. They're kind of snooty. They don't play well with others. All right, they just do their own thing. They're very snooty, so they're noble. Next to that is group 17. Those are the halogens, and then group 16. Those are the chalcogens. All right. We talked about blocks. I have that on the next slide here. But before I jump over there, right, this chunk in here is called the transition metals, right? And dangling off the bottom, which is not on this periodic table, right? These are called the lanthanides and actinides. So the top row here is the lanthanides, and the bottom one is the actinides. So this shows you the blocks that we talked about earlier. So S, P, D, and F blocks, right? So yeah, you needed to know these when we started doing electron configurations as you're cruising through here. When you're filling up these things, so when you get like 4s1, 4s2, it goes to 3d, right? So that's why these are the period -1. So cool, and so on. And then the F block, that's where you start here like 6s, then it goes to 4f, then back to 5d. It gets all crazy now. And this, again, this is an old table because all of these elements now exist. So it's kind of funny. Like they're missing on here, but they're all there now. On the table, most of the stuff you're looking at are metals. I said mostly metals on the table. There's the nonmetals on this corner. So this corner is your nonmetals, except for hydrogen. That's the only one that's not over here. So that hydrogen's over here, so it's a nonmetal. So all the nonmetals over here. The rest of the stuff is metal. This little staircase divider that's in red, it separates your metals and nonmetals. And these green ones that kind of run along the staircase divider, those are the metalloids. They're not quite metals. They're not quite nonmetals. All right, so what makes a metal a metal? It's shiny, it's lustrous, it's a good conductor of heat and electricity, and they tend to lose electrons. All right, that's kind of in a nutshell what makes a metal a metal. Nonmetals are kind of the opposite. They're not malleable or ductile. If you hit a solid nonmetal with a hammer, it's just going to shatter. They tend to be brittle. They're bad conductors of heat and electricity, and they like to gain electrons. Things right along the middle here, these metalloids, right, with the exception of aluminum and polonium, those are just straight metals, right? But all these other like green ones, they're metalloids. They have properties of metals and nonmetals. So they're like a little of column A, a little of column B. They're not quite sure what they're doing, but they're kind of a mix of that stuff. All right, let's get to the trends. All right, this is kind of like the nitty-gritty of this whole chapter. It's the trends. So we can make predictions on things based on where they are placed in the periodic table. And so the big one here is the atomic radius, how big something is. So if I'm looking at the atom, how big that thing is. The trend is that it decreases going across a period and increases going across a group. So when I say it decreases going across a period, that means as they go from lithium to beryllium to boron, carbon, nitrogen, and so on, the atoms are getting smaller and smaller and smaller and smaller. It's like neon is the light in a lighthouse. Ta-da! And it's shining out over the stormy sea, right? It's big on this side, and you get smaller and smaller and smaller. So as you go across that periodic table, right, the atoms are getting smaller and smaller and smaller. And this works for every one of these rows, right? So every period, you're going to start here and they'll get smaller. There are some hiccups to it every now and then, but it's just a trend. So the general trend is you get smaller as you move left to right. So as you go right, they're getting smaller. The atoms are getting smaller. The other group was that these things get larger going down a group. So I started thinking of things that, what's small at the top and big at the bottom? a tree. So like a little Douglas fir tree here, right? So small at the top, big at the bottom. So think of all of these groups as trees, right? Skinny at the top, fat at the bottom. So as you move down a group, they get bigger and bigger and bigger. Let me, while I'm thinking of it here, well, here's a nicer picture of more accurately depicted sizes. Why is it getting smaller? Like as you go from sodium to magnesium to aluminum to silicon and so on, like why does it get smaller and smaller and smaller? What's happening in the nucleus? Like how is sodium and magnesium, how are they different, right? Sodium's got 11 protons. This has 12 protons. This has 13 protons. So the more protons you have in the nucleus, the greater the nuclear charge. And that increasing nuclear charge just keeps on pulling and pulling and pulling them all in. So even though, yeah, these, as you move along here, everything has another proton in the nucleus, another electron on the outside. That nuclear charge is just getting stronger and stronger and stronger until you fill up that entire shell. All right, once you fill the shell, dink, you got to go to a new shell. So like once you go through like the third shell here, so 3p, once 3p fills up, the next place to put an electron is in 4s, right? So that's much bigger. So as you're filling the fourth shell, then it kind of repeats. So that's also why it gets larger going down. So as you go down a group, each one of these, you're filling the next energy level, the next principal quantum number. Boom, boom, boom. And that's really what this this represents, the principal quantum number, right? So the number, the period in the periodic table, that's your principal quantum number. Yeehaw. All right, couple more things here. I want to relate them. So these are all related to size. So if you can remember the trend in size, you can connect that to ionization energy and electron affinity. So the ionization energy is the energy it takes to remove an electron, right? You're going to kick an electron off of that thing, right? The electron affinity, it's a measurement of how willing something is to gain an electron. So what they do is they go in a lab and they'll force an electron onto something and they'll measure how much energy is released when that happens. The more energy that gets released in this process, the greater the electron affinity of that element. So let's first talk about ionization energy. All right, so let's say I have a lithium atom. All right, I need to go in there and put some energy in it. I need to like rip off an electron. I need to take this electron away, right? That takes a certain amount of energy. Right? The closer these electrons are to the nucleus, the harder that's going to be, right? I'm just gonna like flipping through things kind of quick here, but I want to get to this one, this big old thing here. So if I have an electron way out here, it doesn't see the nucleus very well. There's also something called shielding, which we don't mention much in this class, but these electrons on the outside, they don't see like that full tilt nuclear charge as well. They're pretty far away and they're not as strongly attracted compared to a smaller atom where the outside electrons are actually a lot closer to the nucleus. So the larger the atoms are, the easier it is to take the electrons off. The smaller the atoms are, the more difficult, the more energy it takes to remove an electron. So let's put that, good golly, there we go, click, click, being all sorts of crazy. All right, so the ionization energy is going to decrease down a group. So as these things get bigger and bigger and bigger, it gets easier and easier and easier to ionize it, all right? As you go across the table this way, right, they get smaller and smaller and smaller, the ionization energy increases. So it takes more and more energy to pull electrons off, the smaller those atoms get, all right? So here is a graph that shows ionization energy as a function of atomic number. So you see like lithium, right? Pretty easy. Then as I go across all the way to sodium, so I'm starting at lithium, going all the way across to sodium, you see the ionization energy goes up, 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 bam, stops there. Then I go down to the next row, sodium. Whoopsie, sorry. There you go, sodium. So sodium going all the way to argon, sodium all argon goes up. So as you go across the periodic table, the ionization energies are increasing. There's some little hiccups here. They're not super important for this level of class, but I can just tell you like, this little blip here is because the electron that's getting pulled out is coming out of the P subset instead of the S. And this little blip here is because oxygen, the highest energy electron in oxygen is in a doubly occupied orbital. So like nitrogen by itself would have 3 electrons in the P sublevel. Oxygen has 4. So that fourth electron that went in there is paired up. And so there's something called electron repulsion that helps kind of kick it out of there. All right. So those are the little blips. All right. Last little thing I was going to show you about is electron affinity, right? It's kind of the opposite, right? So I'm adding an electron to it. I'm not taking it away, but look at the trend. It's kind of weird. It says electron affinity decreases down a group and increases across a period. That's the same exact thing I just said for ionization energy. Ionization energy decreases down a group and increases across a period. So if they're the opposites, it's like, what's going on? It's weird. But like when you're putting an electron onto an atom, right, it's going to want to go onto a smaller atom. It's going to release more energy going onto a smaller atom than it is going onto a bigger atom because it's going to get closer to the nucleus. And just remember, the closer those electrons get to the nucleus, the lower their energy gets. And so free electron, zero energy. So the more stuff it releases, the more negative it gets. All right, so the smaller these things are, the closer the electrons are getting to the nucleus. So it ends up following the same exact trend. Pretty cool. So connect it to size, and then just remember these things, and you'll be able to answer all sorts of questions on like, hey, what has a greater ionization energy, or which one of these things is bigger? All right, you can just grab your periodic table and remember those trends, and it's a piece of cake. All right, catch you in the next one. I think I only have one more lecture for this particular chapter, so it's a short one. All right, see ya.